Okay, today in 10.1 we'll be working through significance tests for difference of proportions. So to start, I want you to read here at the bottom of page 619 through page 620. And as you read this example for understanding, I also want you to complete it in your notes, example 3 in your notes. Okay, so pause now, give yourself about 5 minutes to do that. Okay, so for Sig Test, we're checking to see if we can find convincing evidence for difference in two different proportions. In this case, two different populations in schools. All right, so there's two ways we could write this. There is no difference. So let's just say, I'm just making these numbers up. Let's just say there is no difference. This school was 30% or 0.3, and this one was 30%. So if there really is no difference, we subtract it, we get 0. Or we could just say, you know what, H of O, we're just going to say 30 equals 30. All right, so that's up to you, but they kind of both mean the same thing. No difference. All right, so here's what the authors did. When I subtract the two proportions, there's no difference. Or can we find convincing evidence that there is a difference? Or you could also do this. If you're doing this on your own, this is acceptable. Okay, you can add it to your notes if you want. All right, so I basically just added P2 to the other side, added it as well. That should make sense. Okay, and then the parameter was P1 was the true proportion of students who come to school without eating from school 1, and then P2, same context, but from school 2. Okay. Okay, so to get our test statistic, just like that general format in our yellow packet, we find our statistic. What's our statistic? What is the difference in proportions? If school 1 is 35, school 2 is 30, the difference is 5, right? So it'll be 5% minus the parameter. In this case, it's always going to be 0. There is no difference over the standard deviation. Okay? So our test statistic will be the difference. Parameter be H of O, which is 0. No difference. Okay, now we get into something called a pooled or combined sample. I want you to read the top of page 621. About half of 621, and then I'll try to also summarize what they're saying and explain a little bit. Okay, so go ahead. Okay, so pooling can get kind of confusing, but basically what they're trying to do is create some baseline data. Which school is kind of the norm? And we don't really know right now for how many are hungry. What's the norm? So that's why you pool this together for the standard deviation. So here's what you do to pool by hand. You take the count of successes in both samples, and maybe even add this here if you haven't already. So for school 1 had 19, and the other school had 26. So that's a combined 45, and then they took a total of 80 and 150 from each school. So 45 out of the 230. So the pooled proportion is 19.6%. Okay, one school is probably a little above that, and one school is probably a little below that, but it's a combined pooled proportion. Now, we didn't do that for confidence intervals. So don't get too worried about understanding exactly why. You won't really be tested on that. You're only going to be tested on when you're supposed to do it. Okay, so why don't you make note of that somewhere down here. We will pool, or in other words, combine the proportions when using a Sig test for difference of proportions, but not for confidence intervals. That's probably worth writing down. I'll pause the video and let you do that. All right, and as you can see now, when you actually figure out the test statistic, notice that PSC is down here. Okay, so yesterday when we did the P1 over N1, then P2, you actually use PSC here. You still use your different sample sizes, but you use the pool proportion here. Okay, and this can get confusing. So when we get to the do step, we'll go through how to do it by hand, but this is a chapter where I have an exception where if you use the tests, the technology tests, that'll be okay for the do step because of the confusion here. The authors even recommend that. Okay, all right, so here we go. Let's turn the page and look at example 4. It's an extension of what we already started here with this, comparing these schools and the hungry children. So go ahead and read through that, and then we'll walk through it together. Okay? Okay, so the big picture is, can we find convincing evidence at a Sig level of 0.05 that there is actually a difference in these population proportions or not? Okay? So if we can't find convincing evidence, we'll we'll, stick with H of O. We'll assume it's believable, that there is no difference. Okay, so here's our plan. Step 1's already done, right? Step 2, to sample Z test for difference in proportions. We don't use a T test until we get to averages. Proportions, we're still using the normal distribution. Okay, 2 independent random samples took place. We're good there. 10% condition. One school had 80, so we're less than, that is less than or we're equal to 1/10 of students at school 1. It's safe to assume that. And then the other one, we had 150 was the sample. We're going to have to assume that that is definitely less than or equal to 1/10 of students at school 2. And we can definitely do the math on that too, because they did tell us more than 1,500 students attended each school. So we're good. That is true. Okay, large counts. Now, you don't have to do the, they actually gave us the counts. One of them said, let's see, 19 and 26 were the successes, right? 19 and not eating breakfast, 26 and not eating breakfast. So those are the counts of successes. And then the failures, just take those away from the sample, right? Because there was 80 in school 1, so 80 minus 19 gives me 61 failures. Sure, I guess you could figure out the proportion, multiply the proportion times the sample, but you get these same numbers. Okay? So these are all at least 10. Is what I wrote down there. Our successes and failures are at least 10. So the sampling distribution is approximately normal. Okay, remember, if these aren't over 10, we might have a skewed distribution. We can't continue on. Okay, so I already named it. We're ready to move on to the do. I'm going to take you through the work here so you know the components of it, but then we'll take a look at the text step. Okay, so school 1, 0.2375, had not eaten breakfast. School 2, 0.1733. So there's a difference, right? Somewhere around 6%. Is this statistically significant? We're going to find out. We're going to put it to the test. So we want to go ahead and get that point estimates. So P1 minus P2, the samples, is 0.0642. Okay, even though I'm going to let you use the text steps, you may need to find the standard error on a multiple choice problem or something like this. So let's go ahead and get the pool proportion. We actually did this on the previous page, so if you want to make this shorter, just put P of C equals, and we already worked that out to be 45 over 230, which is 0.1957. So you can see how it's kind of in between the two. And so it's the standard deviation of our null hypothesis, basically. Okay, so now the standard error is equal to this. You use P of C when doing this, but then you keep your sample sizes different. Okay, so if you, now, what I'm trying to say here is that there is a difference in these formulas on your yellow packet too. So special case, when P1 equals P2, because you're using a pooled proportion right here, P of C and P of C, they were giving you this one. They kind of factored it out. So this is essentially what we're doing on paper right now. Okay, because this is the same, right? P times 1 minus P is the same. But it still says 1 over N1, 1 over N2. Okay, so just another variation you could show when pooling. Okay. All right, so the standard error is 0.055. Now we can finally find our test statistic. So here we go. It's basically ended up being our z-score. So that difference of 0.0642 minus 0, because that's the null hypothesis, all over our standard error, 0.055. It gives me 1.167. Okay, so just a quick recap. We got our difference of proportions. How big was that difference? Obviously it's not equal to 0, but how far off from 0 is it? Is it significant? That's why we're finding the test statistic this way, and we had to go find our standard error. This is a two-sided test, so we have to find the area in both directions, being off by 6% to the right and to the left, or a z-score of 1.167 to the right and to the left. So you do have to double your p-value. Okay, so to get the p-value, you want to state you're using table A, fine, use table A. Normal CDF gives me 0.122, but I didn't double that. So then I made note of it here. I double for a two-sided test, so it ends up being about 0.24. Okay, pause at home if you need more time. All right, so here's our conclusion. Since our p-value is greater than 0.05, this is not significant, right? We're looking for something that's more rare than that. This isn't very rare to be off by just 6.4%. So we fail to reject H of O because we did not find convincing evidence that there is a difference in the true proportion of children who come to school without breakfast between these two schools. Okay, so go ahead and read this to yourself. Just another little recap of what this means, the p-value. So yeah, in summary, we'd get a sample that larger, about a quarter of the time. It's not enough. It's not convincing enough evidence, okay, to reject H of O. All right, so let's take a look at this AP exam common error that the authors are talking about here. It's basically saying when you're done, some students are done using the two-prop z-test. They try to show additional work by stating a formula or showing numbers substituted into a formula. This often results in loss of credit because they use the wrong symbols. There's just a lot of opportunities for mistakes in all of those procedures in the do, as you just saw. So for two sample procedures, I'm going to recommend that you guys just go ahead and use your calculator. Go back and check your work if you have time. Okay, so let's give it a try. So I want you to find two-prop z-tests, plug in the information it's asking for, and then we'll look at the summary screen together to wrap this up today. Okay, and apply it to the last example. That's the information we're going to plug in. Okay, a lot of P's here to figure out, but they got them with the hats on there, so that shouldn't be confusing. And then this one, I wish they put a C there, but they didn't, but it's the pooled one. Okay, the one that does not have the hat over top of it is our p-value. All right, everything matching up. And then there's our test statistic. So you just got to report this stuff. If you use this, name it, and then make sure you record the stuff and record that as PSC right here, okay? These SIG tests can be one-sided. The one we looked at was two-sided. The example that involves an experiment tomorrow, they might say, is the difference less than 0 or greater than 0? And then that just changes our null hypothesis to that, okay? So there is one in your OTI today that is one-sided. Just wanted to make sure I cleared that up. It obviously is possible. You don't have to double your p-value in that scenario, okay? Okay, number 10 is going to be a confidence interval, so we can separate those procedures. This is a two-sided SIG test on these two. 21's a one-sided SIG test, and then here's some good tests like multiple choice questions. So we have two SIG tests, one confidence interval, okay?